Okay, right now I'd like to introduce today's webinar presenter. Mark Wheeler is the Global Director of Systems and Service at Chromalox. He has 20 years of experience in electric process heating with a focus on developing customized solutions for new plant installations and expansions. Notably, Mark and his team have secured an explosion-proof certification and design patent for tank-flanged immersion heaters and introduced DirectConnect as part of its extended technology platform. He is currently responsible for the global product development for industrial heating equipment with a primary focus on energy-related markets. So Mark, welcome to today's event. It's great to have you here. And with that, I'm going to pass things over to you to get us started. So Mark, go right ahead.
Okay, welcome everyone to our presentation today. We're going to review Chromalox's DirectConnect technology and more specifically how we leverage that medium voltage power for an efficient heater design. So we're going to start off just giving a little bit of background on Chromalox and what DirectConnect technology is, and then we're going to dive into what makes it such a great power source to use in efficient designs, and then finally wrap up with some market applications and some real-world experiences with how it can be used to save money. So Chromalox has a background that actually stretches over 100 years, and it all begins with our founder, Edwin L. Wiegand, who was granted one of the first patents for a metal sheath heating element. And for the next several decades, he's discovered not only new technologies, but new ways to apply that heat in a varying amount of products and applications. And we have a lot of really interesting applications that stretch from the military to the space age to more recently in solar and alternative energy. So after 100 years, Chromalox has grown to be the complete provider of thermal solutions throughout the industry. We're actually still located in Pittsburgh, Pennsylvania, but we have a worldwide based manufacturing and sales offices, and we provide one of the widest range of electrically heated products throughout the world. We have three core business segments: our industrial heaters and systems, which is more of our traditional. We also have a component technologies that offers for industrial equipment manufacturers, and we have our heat trace line, which provides temperature management solutions for piping systems, valves, and tanks. So the traditional heating market is roughly divided into two main segments. Low voltage, which has been traditional heating, is used for most applications at around 5,000 kilowatts and below. And then above that is more when fossil fuel fired systems come in demand for the larger heating systems. And the reasons for using fossil fuel are plenty. And when industry first started growing over the years, the supply for coal, oil, and gas is very plentiful. It was easy to get to. And then over the years, there's been a lot of familiarities with centralized systems. And again, in the past, there haven't been as many restrictions on the pollutions and the stacks that come out of there. And as well as with third parties, that's kind of grown up with the industries and become more prevalent. But there's a large infrastructure out that supports it out there. And so that's part of the reason fossil fuels have remained so prevalent in industry. However, the industry has really been changing, not just in the last few years, but really over the last few decades. So as the economy keeps growing, there are expansions and additions, but the majority of people now are much more aware of pollutions and concerns, and they don't want the stacks and the pollutions being done in their backyard. In addition, with governments and agencies, pollution and greenhouse rules have become more complex, they've become more strict, and the permitting process is all increasing costs of these. So that's the reason a lot of the industry is turning back to looking at electric heat, because it eliminates those on-site pollution concerns. And that's where medium voltage can really help provide a low-cost solution out there, where you get all these benefits of electric heating, but can apply it locally for you. So electric heat offers a lot of advantages over fossil fuel-fired systems in the industry. I mean, starting with, there is no concerns of an open flame. So electric heat is much easier to use in a hazardous located and can be used as a point of use. Also, electric heat is very minimal maintenance compared to a fuel-fired system. There's no concern about soot or adjustment of burners or flames. And then also with electricity, it's a very controlled pricing. We all know globally in the last several years how fossil fuel and natural gas have all fluctuated up and down depending on different global impacts, where electricity is locally generated and can be agreed upon pricing years in advance. And then really the big issue is, again, with electricity, you don't have to worry about the pollution stacks and the on-site maintenance, you have a very clean operation, a very low installation cost. And then lastly, with electric heat, you're essentially converting 100% of that power into thermal energy. So you're able to very precisely control the temperatures and the operation of the equipment. And that's really what makes medium voltage such an exciting new opportunity for an efficient heater design, because if we look at in the past at how the profile was, there was a pretty clear split between low voltage and gas and steam usage, and now medium voltage crosses not only some of those intertwining applications from a kilowatt standpoint, but it stretches even further up there into a practical design for large heating applications. Okay, so I thought the easiest way to start with the presentations would to show you some pictures of a traditional low voltage system in the 10 megawatt range. And if you draw your attention to the upper left hand picture, you'll see on the far left side, kind of the shiny enclosures, that is the control panels used for a low voltage system. But even more so to the right of that, that is the transformers that need to step down from medium voltage to low voltage. So as you can imagine, in a system like this, it's not only the cost of the equipment, but the cost to provide those transformers, the base pad, and the wiring that goes in between them. And you can see in the lower right hand picture some of the wires that need to be set up to travel between the transformers and the heating equipment. Now in this picture too, you can see a little better close-up of the wires. Again, there's multiple panels and multiple transformers, but if you look at the highlighted orange arrows, you can get a sense of the cost of all those wirings, as well as with the labor and burden to install the wiring and the raceway to operate such a system at low voltage. So DirectConnect, how does it save you? By the use of medium voltage, we're able to cut down on the wiring and the installation cost, and we'll show some of the numbers here coming up shortly. But again, in these pictures, if you look at the highlighted areas, this is a 2.5 megawatts system that was used for water glycol heating in a power plant. And rather than having those multiple runs of wires and raceways and transformers, you can see how there's simply one conduit connection to bring that power wiring run into the heater. So again, that greatly simplifies the installation cost and time for such a system, and you can provide all that on one common platform versus the prior system that you saw with multiple platforms and runs in between there in real estate. Okay, so if we just take a minute and say, why does a system, low voltage system, add so much more cost than a medium voltage system? And that really goes back to Ohm's law. We need to determine the amperage for such a system out there, because amperage is really the kilowatts or the heating load divided by the voltage. So traditionally in the past with the low voltage, so now the difference is when we are able to compare a low voltage system with a medium voltage system. Again, the kilowatts or the heating load is going to stay the same, but if we're able to increase the voltage supply to such a heating system, essentially the amperage comes down by a factor of almost 17 times. Again, when we're comparing a system that would traditionally run at a 380 volt, that now can be run at a 6600 volt power supply. So when we put this into practical terms, again, from our case study, first what we're going to look at is a system that needed a little over 3,000 kilowatts worth of power. Now in a traditional system at 380 volts, that would be 4,900 amps. And so from an installation standpoint, somebody would have to put in 63 circuits worth of wiring out there. And that's not just the wires, obviously, but that's the fusing, the termination, the pulling of the wire through all the conduits, etc. Now, if we can utilize 6600 volt design, as you can see, that drops the amperage way down to 285 amps. So rather than 63 circuits, there's only 3 circuits of wiring that needs to be done out there. And that's really what the cost savings is and how medium voltage can be utilized for an efficient design. So in our first case study, we want to look at a refinery that had an issue where they needed to replace a 3,000 kilowatt gas-fired hot oil system out there. Now the refinery had been built about 50 years prior, and again, when it was first installed, they didn't have to worry about pollution concerns or emissions. But with going forward, they were actually up against their emission limits, and they weren't allowed to add any new fossil fuel-fired systems. So again, their choices would have been utilizing a low voltage system out there, which would have been fairly costly. What medium voltage was able to do was maximize the energy consumptions, allow installation of medium voltage equipment at a low price point, and totally bypass the permitting process, as they didn't have to worry about putting in another stack or getting a waiver on their pollutions for the area. So we looked at a case study for them. Again, this was a little over a 3,000 kilowatt system. You can see where the medium voltage product was more expensive than a low voltage product. However, if you look at the next set of lines, that's where you can see a medium voltage system really lowers the overall cost of the customer. They're able to eliminate the total installation price of the transformer, the price of the transformer product, and then also the cost of the wiring drops significantly, because again, if you remember that amperage we looked at before, it's almost 17 times less amperage they have to put in there, and that's 60 less circuits worth of labor and burden. So at an installation price, they were able to save over $800,000 while minimizing any environmental impacts. And with a medium voltage system versus a low voltage system, the maintenance cost is much lower, simply because there's less connections to maintain, less parts to inspect, and less fuses to worry about changing. Similarly, on the product replacements over the life cycle, there's simply less components to worry about during the life of the product. The other very significant savings with medium voltage comes out in the operating cost. As you can see, we're able to demonstrate to the customer millions of dollars of savings over the lifespan. And again, that comes down to the amperage that runs through the wire. So in traditional wires, you can calculate the power loss through the I squared R. Again, that's the amperage squared times the resistance of the wire. So again, in a low voltage system, higher amperage is going to decrease how much power is actually transferred to the process itself. So when we look at a medium voltage system, it actually raises the operating efficiency to over 99%. And again, that's measuring the power that's directly applied to the process. If we look at a low voltage system, because of that amperage loss, it's closer to 85% efficiency. And again, if we look at a fossil fuel fired system, you can a lot of times have way less than 50% heat conversion. And again, that's power that you're actually taking, or energy from the system, and applying it to the process. So with the medium voltage system, you're being not only very precise, but very efficient in your power delivery to your process. So one of the points we want to make is, with an electric heater, inherent to any electric heater, we're able to control the power input utilizing solid state control, sometimes referred to as an SCR or thyristor. And for anybody unfamiliar with that, that is similar to the way a dimmer switch can control a light bulb. We can control the electric power output into the heater into the same way, so that anywhere in the range from 0 to 100%, you're only applying the power that's needed for that process to heat it up. And in a DirectConnect system, there's two ways to provide power. There's a phase angle or zero cross. And depending on your application, the system can switch between those. So generally speaking, a phase angle fire can really cut the wave down to only the power you need. However, it also tends to generate electrical noise that some people may not want in an application. Fortunately, phase angle is only needed during the startup phase of a heater. And what that's used for is to ensure that the mega ohm and any dry out that would be needed to be done can be done properly before the system powers up to full power output. And again, phase angle is only used at very low power, and again, that's more of a self-check. During normal operating conditions, that's where zero cross fired SCR is used. And what that does is it chops the waves up only at the 0 point, so that there's no electrical noise that's generated by the system. But again, a DirectConnect system has both of these installed with every system, and it's able to automatically switch between the two. And that's really what the efficiency is in an electric heating system. And so what makes this really great for any process is essentially it's a smart power control. So you don't have to worry about any overage or underages in an application. You're only paying for the power that's converted to thermal energy. And again, with an electrical heating system, you can have a controller in there that's able to learn from your process, so that you don't have large amounts of undershoot or overshoot. You can really tighten up on the deadband, so to speak, in such a process. And again, with the fossil fuel fired systems, that's not possible. You have turn down ratios, there's startups, there's purges that need to happen, there's blowers in the system that are just inherent to any fossil fuel fired system, where electric doesn't have that. And that's where having that SCR or thyristor control can cut your operating profit another 25 to 50%, and increase those savings over a traditional fossil fuel. So again, what DirectConnect does is save you money on the installation side, on the operation side, on the maintenance side, and on the power delivery side. And that's what makes it such an exciting option to use out there for any type of thermal heating need. Okay, for our second case study today, we're going to take a look at an offshore production platform. And traditionally, offshore is a great place to use electric heat, as there's a lot of point of use applications, as well as with compact design that offshore platforms are always looking for. So in this particular one, it was a floating production platform in the Gulf of Mexico. They needed a large heating, about 2,600 kilowatts worth of heating power for produced oil and gas line. And again, as you know, on an offshore platform, there's space restrictions. It was a hazardous area, but medium voltage was ideal for this case, as with the power generation on the platform itself was at 4,160, which is typical for a lot of generating, so it lent itself to medium voltage. But beyond simply the hazardous location, which we're used to, the reduced space and the weight concerns were actually the number one priority for the customer. So as we started to look through the price analysis for this customer, interestingly enough, it actually came out that the medium voltage, despite the lower cost of wirings, wasn't necessarily the lowest overall cost on the installation. And what that came down to, again, was a lot shorter runs of power wiring needed due to the compact size of a platform. However, although the installation savings didn't show an immediate benefit to one way or the other, it really came down to the weight and the size of the product that was going to be installed in the platform. So interestingly enough, when you actually look at the weight of a medium voltage system as compared to the heater, the control panels, the transformer, and even the wiring itself, that's where it was able to make a difference for the customer. And on an offshore floating platform, it's not only the weight of the equipment, but the structural support that it needs to go in there. So for every pound of equipment, they need approximately 4 pounds of steel or supporting structure in there to support that equipment. So when you look at the cost savings from a structural standpoint to put in there, the installation was actually able to save over $500,000 US for the customer, as well as minimizing the amount of space occupied for the equipment, since the transformer wasn't needed. So when we look at the long-term case, again, the 20-year life cycle, factoring in the $500,000 savings, now the medium voltage solution really began to shine. Not only from the installation savings, but again, the operational savings. As I mentioned earlier, you can see where a medium voltage systems operates at close to 99% efficiency, so that saves them almost $600,000 in energy savings, delivering all that power directly to the process. And then lastly, again, with the maintenance and the replacement part, there's simply less parts to worry about over the life cycle of products, less products to fail. So ultimately, when we look at the life cycle over a 20-year lifespan of this product, the facility is going to be able to save over $1 million utilizing a medium voltage solution for this product. Now again, every installation is a little bit different, every on-site, but this slide is just to give some overall numbers. Again, that if you could have a medium voltage system that runs directly off a 4160 volt distribution system, like the offshore platform, that's where you could save roughly $30,000 per million BTUs per hour. Also, with the wiring is another way to look at it. Again, that's where you can save a little over $4 per amp per foot of wire. And then again, with labor savings, that's 80% and above for a medium voltage system, because those labor rates don't have to be included, again, with a lower amount of wires. Now again, these are estimates based on a feed study. Depending on your wiring runs and your on-site locations, they can be slightly lower or higher, but again, this is to give you some ballparks for if a medium voltage system makes sense for you. Now, when does it make sense to use medium voltage system? If you remember the chart I showed earlier with the traditional low voltage market versus a gas fired system versus a medium voltage. Well, generally speaking, medium voltage depends a lot on the wiring cost and again on the on-site. So just to look at it from a product standpoint, around 1 megawatt worth of heating need is when it begins to make sense to use a medium voltage system out there. Now again, there may be other concerns like permitting, like emissions or pollution stack that start to change that. But again, these are some rules of thumb to help you guide for a medium voltage system. Now, Chromalox, as it offers DirectConnect technology in a medium voltage system. Again, that technology can apply to a variety of products out there depending on your application. These are just some of the traditional ones that you would see in the industry. So sometimes a flange or circulation. Those are used for inline heating, like we saw on the offshore platform. Steam boilers and vaporizers are another application with large loading. The first case study we ran through, again, that was for a hot oil system, but hot oil or water glycol is an application out there that's very common in industry. And then there's also a wide variety of the packaged skids where we'd want to put the heater or fuel gas conditioning panels on one skidded platform to be installed on site. Okay, I thank everyone for attending. That concludes the formal part of our presentation today. We'll also be remaining on the line for any questions that you may have. So we'd be glad to answer that for the balance of the webinar today. Thank you.
All right, Mark, thank you for the presentation. Now let's take a look at some of our questions from the audience. The first question is, what is the decisive criterion to choose between low voltage and medium voltage heating systems?
All right, good question, Dave. I'd say each situation is different depending upon the application and where the install site is. So you really need to consider all the facets before you make a final decision. But just to touch on a few of the more major points to consider, I mean, short term when you're looking at installation costs, there's going to be the total heat output, i.e. the amps that are going to be drawn by the heater, because that'll help determine if medium voltage should be an option for you as well. You also want to take a look at the length of the wiring runs so that you can decide what is going to be the total install cost and the labor associated with such things, because as you saw in the presentation, that can contribute a significant amount of time and money to the cost. And then also, in some instances, it's going to be what service is available on site. Again, as refineries and different industries grow, everybody has different availability, both on their low voltage and medium voltage busing side. So the capacity there may help direct you towards one type of service. And then if you're going to look at a longer term scenario too, there's also the efficiency savings you saw for a payback period. Some capital expenditures look for, or some companies have a certain payback period or ROI they want to hit. Those efficiency savings can really come into play. There's also your operating time you want to consider versus a maintenance shutdown. Again, for certain fossil fuel type systems, they need to be shut down and scrubbed and retooled a couple times a year versus an electric system that doesn't. So again, a few weeks of operating time may help pay back such a system. And along the same lines too, you also want to look at the total sustainability. There's always future environmental and regulatory impacts that can come into play, and so you need to take a long-term look at the equipment and how it's going to be able to function over the life of your refinery or production platform.
Okay, great. We got another question here. So what industries and applications are currently using Chromalox DirectConnect medium voltage heating systems?
Sure. So we probably have a few dozen systems that have currently been installed and have been operating for a number of years now. And it's really a wide variety of any industry, just again because electric heating touches a wide range of applications and industry. So there's really no limit to what industry. To talk about some of the more recent ones, let's say power generation. We've had a few people that use them for standby systems as peaker plants because they need to keep them operating and ready to begin producing electric, at a few minutes' notice. We've also had some power generation facilities looking for Frazil heaters, which is basically keeping water intakes from freezing in colder applications. And power gen has probably been one of the first industries that has been a little more accepting of medium voltage systems simply because of their familiarity with installing such power lines in there. Some of the other ones, just off the top of my head too, we've had some propane superheaters for natural gas on offloading facilities where they need to vaporize some of the systems. And then probably the more recent one, the last one I could think of, is we've had a heat transfer system where we're heating hot oil that's used to refine through a heat exchanger for crude oil in a refinery to heat it up for pumping. So again, we really have a wide variety of applications, just anywhere you're going to use heat. And so obviously there's a lot of industries that can use electric heat there.
Okay, another question that we got in here is, what is the operating efficiency of a medium voltage system?
Okay, so another good question, because in larger loads, or larger heating applications, I should say, there's always a question about how efficient a system operates and how what is going to be the return and the cost of your fuel. And that one's always tough to classify because there's different engineering practices on how you classify efficiency. So the way I would just classify it for the purpose of this discussion is it's the efficiency of the cost of whatever power source you're purchasing, whether it's fuel or electric, and how much of that energy is actually being transferred into heat that's used in your process. Because again, it's not necessarily a burner efficiency, it's the cost to get the fuel there, for pollution control, for startups, things like that. But electric system is relatively simple in that the power coming in, you're getting close to 99% efficiency of that power transferred into heat in your process. So again, there's really only a 1 or 2% loss. And again, that's just through the transmission of the electric there and a little bit of the heat in the outside environment through the application. But again, as you go up in voltages and increase the voltages, just like transmission lines, the efficiency increases to very great levels. So again, that's what we say with medium voltage for the majority of applications. It's been very easy to demonstrate 99% efficiency in these applications.
Okay. Also, another question here. Can a medium voltage system be located in a hazardous area?
Oh, yeah, good one. So, again, electric heating in general lends itself to being able to provide very localized heating and sources in applications so that, again, the source of that heat can be located directly in a hazardous area. Again, so with a fuel-fired system, generally you're not going to want to have an open flame in such an area, or places like a refinery or an offshore platform can cause some issues. So you'd want to have that system located far away. But again, with electric heating, both low voltage and medium voltage, it can be located directly in an area. So again, a medium voltage system can be provided with an IEC, an ATEX, Class 1, Zone 1, similar applications, but it can be located directly in your hazardous area. So again, back to the previous question, when you talk about efficiency, that's why the efficiency can be so high, because again, you don't have to worry about transmitting over long distances. That heat can be supplied directly at the source. So yes, it can be located in your hazardous area with no issues.
Okay, great. We've got time for one more question here. And considering that these heaters are large kW heaters, is harmonic distortion an issue with these large heating systems?
Sure. So for electrical people that are on the line, we do get that question about harmonic distortions, and that has to do with the power switching. The one thing to keep in mind is there's really two different power switching modes we talked about. There's a zero cross, which is what we use for our typical application, and you're not going to have the harmonic distortions during operation. Where it comes into question is whenever there's a startup situation, the heater essentially goes out and checks to make sure there's no leakage current and we don't have any wet elements, so to speak, in the industry. And that's where they use a phase angle firing. So the big difference is when it uses the phase angle firing, it has the potential to generate some noise and harmonic distortions, but it's using a very, very small percentage of that load. It's not firing at the full load. It's basically just using a few percentage points to check the system. And then if it does detect any leakage current, it can go through a set of checks to dry out the element. So again, when you're using that phase angle, it's a very small load. So when that's measured, yes, there's some distortion, but it's very minimal. In fact, it meets, there's a European norm for the EMC standard, electromagnetic compatibility, and it more than meets that, so we can put CE marking on it if needed. There's also an IEEE 519 that's a standard as well, and when you use that phase angle firing, it's well below the allowances in that system. So again, that's only for a startup condition, but again, at the full operating loads, we're operating at 0 cross, so any issues with harmonic distortion go away.
Okay, well, we're going to wrap up the Q&A. Once again, Mark Wheeler, thank you for your presentation and your time today. And thank you to all of our audience members for joining us, and have a great rest of your day. Thank you.